Sequences. Sequences are some sort of array of information with separate entries or separate terms, we might call them, separated by commas, versus series are a sequence of terms that are being added together. So sequences are just a accumulation of or a set of terms separated by commas is one way of thinking about it, whereas a series is separated by additions or by adding. A sub n is going to be notation, and we're going to kind of think about A sub n like function notation. We're going to think about A sub n as kind of like A of n. I'm not going to normally write it like that, but that's kind of how we're going to need to think about it, like f of x. A of n or A sub n, we're going to call the nth term. So if I were you, I would go ahead. We're going to be using this quite a lot, this entire chapter 9a, 9.1 to 9.5. So when I say A sub n, or when I say the nth term, those are synonymous. And if you guys look up in the list of terms right up above, you see A sub n, right? Why would it make sense that I need to call him the nth term and not like an actual, who's this guy? The first term. Does that make sense?
Yes.
Which term? The first term. What term is this?
Second term, third term, fourth term.
Why is this the nth term?
Because it does not put any number.
Yeah, I'm not sure where it is, right? I just know it's somewhere down the line. Now, when you guys talked about sequences last year, wasn't there usually some sort of pattern as to where the next terms would come from? Okay. So we're going to have to be looking for some patterns today. Just a quick heads up for 9.1. 9.1 introduces the whole idea of sequences in series. The whole idea. 9.2 and 9.3 and 9.4, 9.5 is a little bit separate, talk about special sequences in series, arithmetic and geometric. They should have been ones you saw last year. But there are way more sequences in series beyond arithmetic and geometric. So in Precalc, we zoom in on these two really special ones. In 9.1, we just kind of show the entire field of, not the entire field, but we show you lots of different sequences. Some are arithmetic, some are geometric, some are neither is what we would call them. Let's just put it this way. Calc BC spent, I don't know if I'd say the majority, but spent longer than any other topic this semester on sequences in series. So there's a lot more out there. Does that make sense? So 9.1 kind of shows you, like, there are all sorts of different types of sequences in series. 9.2, 9.3, 9.4 say, let's zoom in on these special ones that we can handle simply. But there's a lot more out there. So 9.1 might kind of be one of the hardest sections of the chapter, not because what you're supposed to do is really hard, but because it kind of introduces you to harder topics that you're not going to really have to master yet. Does that kind of make sense? So since it introduces the entire thing, and we're not going to really even need to master the entire thing, 9.1 at some places might get a little confusing, like giving you a sequence and saying, hey, come up with a formula that models it. And you're like, I don't know. When we get to 9.2, 9.3, 9.4, they're going to all be following certain characteristics, and we'll kind of get patterns to use, formulas to use. But in 9.1, you might just have to kind of be like, I'll try to help a little bit today and tomorrow. But once again, you don't have to necessarily master in 9.1 every sequence in every series. It's really hard to do that, and even in BC, they're still kind of figuring it out. Really quickly, the very, very, very bottom, the domain. Wait, domain, that word, what's it normally stand for? Domain X, right? The X values. Oh, but we don't have X's. But we do have N's. N's are allowed. Why would it make sense that N's can only be positive integers? And if you guys don't remember what integers are usually the positive, negative counting numbers, not fractions, not rationals or irrationals. The integers would be something like n is equal to. But this little note says n can start at 0 or 1, depending on the problem that you're being given. Why does it make sense, though, that n can only be these numbers and can't be fractions and can't be decimals? Why does that make sense? How can that make sense? I'm going to check the thermostat real quick. I see you guys freezing. But why does it make sense that n can't be a fraction? Why can't n be 1/2, for instance? N represents the term, good. And what's not going to be true about a half? Half isn't an integer. You guys are right about that. But also, doesn't n stand for which term, like the nth term? Is there going to be a 1/2 the term? Is there going to be a 3/4 term? Is there going to be a 0.765 term? No. So if it makes sense that n has to be which term we're looking at, then maybe it makes a little sense as to why n is only going to be 0, 1, 2, 3. I think when we go to graph these, we'll talk a little bit more about that whole idea of n only being integers. But for right now, let's just say, okay, a sub n, nth term, can be given by a formula, 3n minus 2. Do you kind of see why I said that you can think about a sub n as he might be given a little function. And the little function might have a variable, but instead of x, it's going to have n. So how do we find the first term if that's our formula? Just plug in 1. A sub 1, n is 1, fine. Plug it in the n spot. So 3 times 1 minus 2 is just going to be 1, right? Whoa. Mind blown. What are we going to do for the second term? Plug in 2, right? And then, do we know what's going on now?
Yes.
Okay. What pattern do you see with the terms, though? They're going up by 3 every time. Can you guys tell how they're going up by 3? My little very easily distracted ones. I mean, you can see it here, but can you see it here? You're multiplying by an additional 3. So does it make sense that 1 times 3 is only 1 3 minus 2? 2 times 3 is 2 3s minus 2. 3 times 3 is 3 3s. What's being added every time when the multiplication goes up? An additional 3. Because multiplication is just repeated addition, right? Multiplication is just repeated addition. So yes, it is sometimes, and actually to be honest, usually easier to actually get terms and then look and say, hey, what's the pattern? But maybe some of you will get to where you actually can look at the formula and say, oh, hey, it's going up 3 every time. That's kind of cool. And just a quick little heads up, even though it's a whole section early, if we ever have a sequence where you are always adding a constant, you're adding the same constant over and over and over again. Does anybody remember which is which? Whenever you're adding a common difference, whenever you're adding a d, like this one, we're adding 3. Is it arithmetic or is it geometric? Yep. You can think you learned arithmetic before you learned geometry. Addition's easier than, does anyone remember the other pattern? Not adding by the same, but it's multiplying, which ends up repeated multiplication will use powers. Does that kind of make sense? Repeated addition shows up as multiplication. Repeated multiplication shows up as powers. But yeah, this one is technically, some people call it an arithmetic one. I don't like that as much because I don't see an A in there, and we already say this word is arithmetic, but whatevers. Arithmetic. This is coming back in section 9.2. This is one of those special ones that we can actually memorize formulas for as to how we can always get to like the 10th or 50th or 100th terms, how we can find partial sums and all that crazy stuff, but we'll get there. We'll get there. For right now, if you're given an nth term formula, if you're given a formula for the nth term, just plug and chug, and then you can get your sequence and find a pattern if you need to. So there are 2 different ways of defining sequences. The way you just saw, we would technically say that the sequence is given to you, we could call it explicitly. We could say explicitly. If the formula is given to you, we could say it's an explicit formula. There are actually 2 different types of formulas. If they give you a sub n, as a function of n, which is what you guys just saw, technically that would be an explicit formula. And that's normally how you're going to see it. That's just not always how you're going to see it. You could say explicitly defined. I'll just call it explicit. It's an explicit formula. They're giving you a formula that encapsulates the entire sequence all in one shabam. You can plug in 1, you can plug in 10, you can plug in 50, you can find any term you want, just plug it in. There are more hidden formulas, and we'll talk about it in a little more depth in a page or two. But there is another type of formula called recursive. And recursive, just for sake of argument, I'm going to use a different letter than n, even though it technically could be the nth term, but the nth term, we're going to attach it more to f of n, the explicit formula. Let me call it a sub k. Same idea. Just talking k would be the kth term. But with recursive formulas, sometimes they do a sub k instead, and then they give you some sort of function in terms of a sub k minus 1. Whoa, 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 whoa. There's a minus 1 down in the subscript. You guys know what I mean by subscript, right? Okay. There's a minus 1 down in the subscript. So if this is, for instance, solving for the fourth term, what would I need to look at to plug in? 4 minus 1 would be the third term. To get to the fourth, I need the third. To get to the 10th, I need the 9th. To get to the 100th, I need the 99th. Recursive formulas say, I'll get you there, but you're going to have to go step by step. Explicit says you can jump to the 10th or the 50th or the 100th, which is really helpful. Recursive formulas say, no, you got to do all the jumpity jump, 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 jumps. You got to do the pattern over and over and over to get there. I'll show you the pattern, but I won't let you go straight to the term. Which can be super, super nice if the pattern is easy, but the formula is hard. Or if you can see the pattern and you can't see the formula. So in section 9.1, it can be really nice, except is anyone going to want to repeat a pattern 50 times to get to the 50th term? Probably not. Now, if they gave you 4 and you need to get to the 6th term, I can do a couple jumps and I'll be all right. But if you have to keep track of all these jumpity jump jumps 50 times in your calculator, that would just be super annoying. So recursive is actually really good for programming. And there's a type of programming that uses recursive formulas or recursive steps. And the reason is, even though by hand, jumpity jump jump jumps can be super annoying, with technology, jumpity jump jumps can happen like this. Does that kind of make sense? You can program a computer and it can do the jumpity jump jump jumps super fast. Where by hand it would take a long time. So recursive is really nice for programming. It's just kind of annoying by hand. These are the two different types of formulas. That's when you're given a formula or you need to find a formula, use a formula, but sometimes you're just given the sequence. And so you're just checking out what they've already given you. And that's when you're looking at the terms and trying to find patterns and maybe using that. If they give you a sequence, sometimes they're going to ask you to take that sequence and go to a formula. And remember, in 9.1, it's going to be hard because we haven't zeroed in on these two easier types, arithmetic, geometric, yet. So you're just going to kind of be feeling it out, being like, I don't know what the formula is. I'll see if I can figure it out. But that's not all of homework. That's only a very, very little bit of it. Here's one of those examples. They say, here's the sequence. And you're like, great. Write it down. Think about the pattern. Just think about the pattern. At the end of the day, we want an a sub n formula. And some of you already realize what they're asking for, and you're already trying to play around with, okay, what formula could I plug n in? N is 1, n is 2, n is 3, and get those numbers out. The rest of you, it's okay. Just write it down and say, I wonder what the pattern is, how to get from one term to the next. Anybody have a pattern for me? Joel. Good. You're always adding by 2 more than the last. And if you guys notice it, you're always adding by what kind of number? Okay, so you're always adding by increasing odd numbers. That's the pattern. And the pattern, think of it kind of as the recursive formula. I mean, we haven't written it recursively yet. But the pattern would say, oh, well, once I figure that out, if they were to ask me for something like 1, 2, 3, 4, 5, the 6th term, that wouldn't be too bad, would it? You already have 5 terms. How would you get to the next term if they needed it? Add 11 to 24, right? What if they asked you for the 8th term? Okay, fine. Add 13, then add 15. What if they asked you for the 25th term? Okay. So recursive formula, because we see the jumpity jump jumps, let me show you what the recursive formula would look like. The recursive formula, if it wasn't just finding the pattern and we, like the 25th, we're like super annoyed at that. The recursive formula would say, okay, take what Joel saw, adding odds, and say, okay, how can I write down a formula that shows adding odds? I could say A sub is going to equal, I'm going to get to the next term by taking the previous term. Previous term needs to be minus 1. I can get to the next term by taking its previous term and then adding, okay, what am I going to add? I can't just write odds. But I could say 2n plus 1. Now, hold on. I did just change the n for a k, so I'm going to make it 2k plus 1. But let's see, first of all, why Lainey and a few others. I think this might have been from last year. I think our new textbook has helped us out in this chapter. People never used to get that so fast. 2k plus 1. If I just put 2k, 2 times 1, 2 times 2, 2 times 3, those would be the evens, right? Okay. When I take an even and add 1, what am I always going to get to? An odd. So 2 times 1, 2 plus 1 is 3. Do I start off adding 3? Yeah. If I started off adding 1, then 3, then 5, I'd do 2k minus 1. Because 2 minus 1 would be 1. 2 times 2 is 4. 4 minus 1 is 3. But since I needed to start at 3, 2 times 1 is 2 plus 1 is 3. 2 times 2 is 4. 4 plus 1 is 5. 2 times 3 is 6. 6 plus 1 is 7. Okay. That would be the recursive formula. Except, recursive, here's the struggle. This just tells me add 3, add 5, add 7. There's one big question or one big piece of information that's missing. We have the pattern, but we don't know where to start or end. Start or end. A sub 1, I have to tell it where to start. Because couldn't you add 3 and 5 and 7 to 0 or add 3 and 5 and 7 to 1, add 3 and 5 and 7 to 21, and it would be totally different sequences, right? Same pattern, but a different sequence. So we had to say, okay, we need to start at 0. You have to have a starting point for recursive and then say, okay, start here. All right, now jumpity jump, jump, jump. I want you guys to open up your calculators. And I want you to change the mode to SEQ mode. Sequence. Open up your calculators to SEQ mode. And then go to your y equals. That's where things change in modes, right? SEQ mode. Ooh. Mode, and then go down to where func is. Func, and then par, and then pull, and then SEQ. Sequence mode. Func is function, y equals f of x. Oh no, mode, sorry. Mode, go to sequence. Now go to y equals.
Wait, should we be in radian?
It doesn't actually matter unless we start doing trig, which we're not going to. So you're okay. Have you guys figured out where my n came from? Have you tried hitting this button yet?
Oh, yeah.
It's only x in function mode. It's n in sequence mode. And hey, do you see how n's actually on the button?
Yeah.
I bet the t and the theta have something to do with the other two modes, the par and the pole. Anyway, coming back. So the n we'll get just by typing in, right? Now up here, I have typed in a certain sequence, but hold on, we just did one a second ago. Didn't we do 3n? What was the one we just did? 3n. The example we did with a sub n, not a sub k. Oh, 3n minus 2. It was the one from a couple pages back. So just so that we get a feel, before the recursive is actually a little harder to figure out for the first time. But 3n minus 2, I just plug in the function. I'm like, oh, sweet, a sub n equals 3n minus 2. N min is whether n starts at 0 or 1, but in all of ours, we're pretty much going to be starting at 1. So you can just go ahead and pretty much always have a 1 in there for the first term. Sometimes in like physics, you might want to start at 0, like the 0th term, like when t is 0, initial. Anyway, but for our purposes, n is 1, the first term. But it's also always going to ask us for the n min, meaning u of 1. It's always going to ask us for the first place to start because it's a program and it's used to needing to be given information recursively. The ironic thing is if you guys actually say, hey, can you start this pattern at 5? The crazy thing is, since you said a is 1, or sorry, n min is 1, if you guys went to the table to go check out this sequence, it started at 5, but then it ignored you for the rest because it's not doing a recursive jump. It's just saying when n is 2, n is 3, n is 4, n is 5, n is 6. So it listened to you for one term and then it ignored you for the rest. So when you're doing an nth term formula, this bottom part is important because, I mean, you should make it what it needs to be, but it's not going to actually change the programming as to how it gets the second and third and fourth terms. You just plug in and it solves. Guys, what should the first term have been? It's not 5. Yeah, if you plug in 1, 3 minus 2 is 1. The first term should be 1. And now we should be good because it's like, okay, fine, 1, and then it plugs in, plugs in, plugs in, plugs in. Was that the sequence that we had? The first sequence? I think so. Nick, go ahead.
What's the difference between the first n min and the second?
Because the first n min is just asking us, like, what's your lowest n? And for us, since we're saying we're going to start at n equals 1, the first term, that's just saying start at 1 for the first. But this is saying give me the actual term that's in the first term spot. So for instance, for this one, I didn't start at 1. I mean, my first term, n was 1, but what was my actual first term? 0. So I would need to put 0 as the term that was there in the u of n min. But here's the dilemma, guys. I don't have an nth term formula yet for this sequence. All I have is this recursive formula that says, well, to get to the next term, you got to use the previous one. Let me show you how to do that in the calculator. Freezes. Let me come back and play with it. Are your batteries such that you can take them out, or is it like the screwy thing where? Oh, okay. Chris, what's up?
Yeah, mine is like Nick. Mine says error. Right, plug it in.
Oh, you can't do decimals in this mode, remember? So you need to go ahead and change your window to be automatic, not, sorry, yeah, auto, not ask, because you were plugging in 1.1 and there is no term at 1.1. Does that make sense? Yes. Change your window to ask. Oh, it asks you for U1 and U2. Huh, I didn't know that. But it is totally frozen. Quit. Auto. Auto, yeah. Oh, huh? No, yours is right. How are your guys' modes different? Oh, yours is auto. Yours is ask. Hey guys, go to your window real quick and go to automatic, not ask. A lot of you guys are in ask from an old example that we did. Go to auto, not ask. There you go. What does it not like? Oh, there we go. You had like a weird number in your window, so it was freaking out trying to get there. But now you're good. All right, guys. Do you see how the U is really just representing the A? Are we okay with that? U is like A. U of N is like A of N? Okay. So if I need U of K to be... What's wrong, guys? Did you plug in the 3n minus 2 and it's not working? Okay, let me show everyone else exactly how to get this recursive formula. And then I'll come over and try to work with your guys' calculators. U is representing A. So when this one says A of K, we could rewrite this for our calculator itself. We could rewrite this to be, okay, fine, U of N is what they use instead of A of K. So the A needs to change to a U. The K needs to change to an N minus 1. And then my K is going to change to an N. All right, I've just said, okay, fine. If I have to make this a of k my u of n, I'm going to go ahead and say, all right, I'm going to keep using that notation. So the a is the u, the k is an n. If this writes it in parentheses instead of down here, I'll write mine in parentheses instead of down in the subscript. Change the k for an n. So let's see how we can get that into our calculator. Does anybody see a little u anywhere? The n is going to be this button, but does anybody see a little u? Not a capital U, but a little u. Second 7, exactly. Second 7 is talking about this u, the u that talks about the a sub n formulas. I'm going to put a parenthesis and do n minus 1 to denote the sub k minus 1. And then I'm going to put in my pattern that you guys saw of adding the odds, which is going to be 2n plus 1. And then I want you guys to go check out the table and see if we have our sequence. Okay, whose calculator wasn't working? Okay, that's good, that's good, that's good. Oh, that's good. That's not. Oh. In your table setup, you have it going 10s, go by 1s instead.
Oh, my bad. Okay.
It was from an old example. I think that's good. So probably table setup. Yeah, you guys are both on an old example that we did. If you have it going by 1s, then all of a sudden it'll count the normal way. Oh.
It's because
Oh, got it. You took it out.
it's different.
It's different. Let me see mine. What's wrong? It's adding 5 and then 7. Where'd the 3 go? Okay, check it. Check it. Give me 1 second. I know we might have some questions about calculators, but the problem is it is generating something, but it's not generating the right something. Somehow we got a little bit off, so our formula is a little bit off. So guys, help out. I needed to add 3 first, not add 5 first. I needed to add 3 first, but right now it's adding 5. What's it doing that's throwing us off? Did I type it in wrong? Because you guys said yours was wrong too, right? Not just mine? Why would it be 2n minus 1 and not 2n plus 1? Didn't we say, wait, but 3 and 5 and 7 makes sense? Don't we already have a sub 1? To get to this term, what would he be? A sub 2, right? Uh-oh. So to get to a sub 2, it wouldn't be plugging in 1. What would it be plugging in? 2. 2 times 2 is 4, and 4 plus 1 is 5. Oh, stink. We were saying, oh, we're going to start at 1, right? No, because there's not a jump yet. There's a jump going to 2, and so 2 is what gets plugged in first to get to the next term. So the struggle was we were actually 1 off. But if you guys go ahead and go change this to 2n minus 1, saying, it's going to start at 2, not at 1. 1 is already done. Then it goes to 2 to keep moving on. Change that to a minus. Then we should be able to go ahead and, if it actually changes to a minus, there we go. Now we should have the sequence. 0, 3, 8, 15, 24, 35, 48. Now here's the struggle. I'm going to come around and see if anybody else has calculator questions, but that's not actually what this entire problem was even asking for. We figured out how to use our calculators, which is cool and all. We kind of figured out how to make a calculator do the jumpity jumps for us, because when we gave it that formula, as it scrolls down, it's adding every time based on the prior one. But it was asking for an a sub n formula. It was asking for like an f of n formula where you don't have to jump to get there. You just plug in n is 1, n is 2, n is 3, and you get out 0 and 3 and 8. Now some of you were able to figure out how to make 3, 5, 7, 9, 2k plus 1 or 2k minus 1, which I'm going to change right now because the plus 1 was 1 off. So don't say anything out loud, but I want some of you guys to be pondering, okay, fine, what formula, not 2n minus 1 or 2n plus 1, that only gave us this. What formula might give us 0 and 3 and 8 when plugging in n is 1, n is 2, n is 3? Jaden, I know you had a question. What's going on, bud? Oh, you don't need to do stat plots. The table is where we were. So second graph is where we're trying. Oh, there you go, except 1, 4. What'd you put in there? U of n minus 1. Oh, we have to start at 0 because 0 is our first term. Oh, no, you want to do parentheses. I'm doing parentheses too. Oh, don't worry, because, yeah, your calculator is doing different notations, so you don't have to worry about the brackets at all. Mine just automatically does the brackets. Anybody else whose calculator isn't working? There you go. So if you had scrolled, you would have eventually gotten there. It just wasn't working. All right, guys, anybody have a formula? Anybody find a pattern? P.S. This is where it gets hard. And this is where we don't have to master. This chapter, we don't have to master this, but this is where it gets hard. What's a formula? If you plug in 1, you get 0. Oh, what about n minus 1? Right? Plug in 1, you get 0. Cool, let's try it again. N minus 1 doesn't give me 3. Okay, so what's another way to get 0 from 1? Okay, so how about 0 times n? 0 times 1, 0 times 2, 0. That doesn't work. But keep thinking. Maybe we shouldn't be working off 0. Maybe we should work off 3. How do you get from 2 to 3? N plus 1? N plus 1 wouldn't work for that one, though. 2n minus 1? Okay, so 2n minus 1, 4 minus 1 is 3. 2n minus 1 would be 1. That doesn't work. See, this is tough, right? This isn't easy. And then this is something that we don't need to master in pre-cal, but you're going to have a couple questions in homework where it asks you to try to find the pattern in a formula. The pattern this way is easier. Oh, add the odds, but here it gets hard. I'll give you a hint. You don't want a 2 times anywhere in it. You do want a subtraction, though. 3 times? But 3 times 6. 6 minus 3. 3 times n minus 3. 3 times n. Ooh! 3 times n minus 3 is 0. 3 times n minus 3 is 3 times 3 is 9 minus 3 is 6. So I'm trying to find out a formula that if you plug in n is 1, n is 2, n is 3, that will get 0, 3, 8, 15, 24. And here's why. Let me show you why, real quick. You can keep thinking. If I wanted to get to the 25th term, it'd be super annoying for me to keep adding. But couldn't we scroll down to go get the 25th term? Yeah. Or maybe we could even use our calculator, which is really, really cool, and see if, now that we've changed modes, if our variables are different. And we could maybe do y1, let's see if it works, of, let's see, when n is 25. Ooh. That doesn't seem to make sense though, right? Okay, I think this is looking in function mode, so that doesn't work. But I could go to my table and I could go ahead and scroll down to 25, or maybe I could actually go here. Some of you guys realize that if it says ask, it won't show you anything because it's waiting for you to tell it what you want. You could say, hey, can I have the 25th term, please? Oh. Can I have the 500th term, please? Why is it taking a little bit of time? What's it literally doing? Why is it taking? It's literally saying 1, 2, 3, 4. It's literally going to 500. Now, it did 25. Oh, that didn't take it very long. How long would it have taken me? You? Forever, right? Because you would have had to keep count and add higher and higher odds. The calculator is literally adding and doing the pattern to get there. Nick? Well, let's check it. I actually don't know if it, because technically with ask, I think it's going to think because it needs to do each process independently because it can't tell what you're going to do. Does that make sense? I think it did. I think it was about the same. Pause. Pause, pause, pause. But what if we had to do it by hand and we couldn't use a cool calculator or we were having struggles programming it? How do you plug in 500? I don't want to jump to 500. I want to plug in 500. That's why this formula is so great. I want to plug in 500. Do what, though? No one found the pattern? What numbers are really, really close to 0, 3, 8, 15, and 24? No? No? There's a certain special type of number that's one away from every single one of these. Squares.
Oh my goodness,
Such an easy formula, and yet you thought of it? So what if I wanted you to find the 500th term if you knew this? Oh, easy. Just do 500 squared minus 1.
Oh, that's easy. Oh, wait, that is easy.
So recursive is great for computers to be doing, but we don't want to really have to recursively do anything past a couple jumps. But if we can find this formula, which is really hard to find, and you do not have to master, try it in homework when they ask for an nth term formula. But in sections 9.2, 9.3, 9.4, we'll have very special sequences and series that always get nth term formulas the same ways, and so we'll just memorize those. So remember, these are going to be kind of hard, but you don't have to master them. This isn't the point of the chapter. It's just an intro to, oh, in order for me to do this by hand, it'd be way easier to have a formula to work with. I'm going to get you guys writing this page of notes as I go ahead and answer Jacob's question. Go.
So I think I would have seen that a lot earlier
If.
if I didn't look at the pattern by adding to.
That's a very good point. Because a lot of you guys, and that's how my brain does too, we see the pattern, like Joel saw real quick, right? It took him a few seconds. Like +3, +5, +7. But once you see that, you're like, oh, it needs to use odds in the nth term. It didn't use odds at all. It was an n squared minus. So sometimes they're totally unrelated, the pattern versus the nth term formula. It's an interesting observation. AJ. Oh, you would just, remember how we plugged in before the recursive one, we plugged in 3n minus 2? You would do the same thing here. You would just plug in, instead of having to use the u of, instead of having to define him in terms of a previous one, you would just throw in the n squared minus 1 like you would do a normal function. And when you plug in n squared minus 1, still starting at 0. When you go to your table, since we found the right formula, oh, it's going to be calculating the 500th. Hold on, let's see if it'll go here. There we go. If you guys ever need to get back to normal for your table, just remember you can start it at 0 or 1, and then just change it to automatic. Some of your calculators were mad at you because you had something in there from a previous problem, and so it was trying to do all that work for you, and that's, Michael, that's what was going on. You had like 2,000 something, something, something that was in there, and so it was trying to do all that work. And that's why it got stuck. You could scroll. You can't jump. Now, you could do the plus sign, and I think that lets you jump what you're going by, and you can jump by hundreds instead. But see, Nick, it's working.
But if you were to scroll down to like 500,
It would be jumping by ones, so it would be okay.
Oh yeah, okay, so.
And what I was thinking right now, why I put in 100 is that way. There you go. So it's done the work for all of them. And so it found a pattern, and it's just going to go ahead and continue it. Yeah. But that's only because it's predefined that it knows what you're jumping by. For the ask, it has no idea what you're going to plug in. So that's a struggle with that. Recursive. Nice thing is, guys, we already talked about it. Recursive, it's the, well, for lack of a better term, it's the jumpity jump jump one. It's the one that actually has to jump to get to each and every. Yep. Jumpity? Yep, I am. It's the jumpity jump jump one, right? It's the one that's going to jumpity jump jump all the way through to wherever you ask it to go. So you'd be having to do it by hand, or the calculator would be doing it for you much, 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 much quicker. But what's going on? Each term is defined in terms of previous ones. And it just describes how to progress from one term to the other, aka it just shows or uses the pattern. And as Jacob already said, the pattern might be totally unrelated with the nth term formula. The pros is usually it's easier to spot. The pattern's usually easier to spot. It's harder to program. It's harder to input. Maybe not program. Harder to calculate. It's harder to calculate for large ends. It's easier to spot, like the pattern that Joel saw, but it's just harder to calculate. And kiddos, the cool thing is, if you write down this example, please make sure you put a -1. My little subscript wasn't letting me do more than 1, which is kind of lame. But you guys have a great amount of information to start homework tonight, but as you, oh, I didn't update your board. Homework's due on Friday. But you should be able to get really far through it tonight. So let's just see where you get stuck for tomorrow. Get out of here, cool kids. We'll see where you get stuck. Whoa, whoa, whoa! Are you cleaning up after yourselves?